Hello everyone and welcome. First of all, I want to thank the organizers of AutoML for the opportunity to participate. I'm Daniel Fernandez Sanchez and I'm going to talk about improved max entropy search for multi-objective Bayesian optimization with constraints. This is a joint work with Eduardo César Garrido Merchan and my PhD advisor Daniel Hernández Lobato. There are many problems where the purpose is to optimize several objectives while fulfilling certain constraints. For example, we could want to maximize the speed of a roll while also we are trying to minimize its energy consumption as well as avoid to break any of its joints. Other example consists to maximize the accuracy of a neural network, minimize its execution time, and we have a limited amount of memory space for the size of the network. Because this type of problems have several objectives, there is no single solution but a potential infinite set of optimal solutions, called Pareto set. The Pareto set evaluated in the objectives constitutes the Pareto front. All the points in the Pareto set are Pareto optimal. One point is Pareto optimal if it's not dominated by any other point. In a minimization context, a point x1 dominates x2 if the values of all the objectives in x1 are all lesser or equal to the values of the objectives in x2, with at least one strictly minor inequality. Also, all the points in the Pareto set are valid. That's it, the values of all the constraints in those points are greater or equal to 0. Here we can see a multi-objective constraint minimization problems. We have two objectives and one constraint. This is the constraint in input space. The red crosses are the Pareto set, and the points evaluated in the objectives constitute the Pareto front. The problems like the ones described before have three main characteristics. We do not have the analytical form of the objectives and the constraints, so they are considered black boxes. Also, the evaluation can be contaminated by noise. And lastly, this type of problems are very expensive in some way. To solve this kind of problems while minimizing the evaluation to perform, we can use Bayesian optimization. Our acquisition function improves max entropy search for multi-objective Bayesian optimization with constraints that we abbreviated as MESMOC plus is an extension of max entropy search, MES, to multi-objective constraint optimization problems. MES acquisition function uses the entropy reaction of the solution of the problem in the function space to conduct the optimization process. This is expression of MES. The first term is the current entropy of the optimum, Y star. Note, because MES only works in one objective problem, the solution is at one point. And the second term is the expected entropy reaction after evaluating on X. Because the computation of the entropy of the solution is very expensive, the authors of MES wrote this expression to this one. Both expressions are equivalent because the mutual information between Y and Y star is symmetric. The final expression of MESMOC plus is equivalent to this second expression, but the outputs now are vectors because we have several black boxes and the optimal solution is now a Pareto front. The first term of MESMOC plus is simply the current entropy of the predicted distributions that we can evaluate using this formula. In the second term, the expectation is approximated by sampling from the Pareto front. And finally, the predictive distribution conditioned to the Pareto front are approximated using truncated Gaussian, obtained by an assumed density filtering. This is the final expression of MESMOC plus. MESMOC is other acquisition function for multi-objective constraint optimization. It also minimizes the entropy of the solution in function space, but its approximation is different from the one of MESMOC plus. Due to its approximation, it optimizes all the objectives and constraints independently of each other. MESMOC is another acquisition function for multi-objective constraint optimization. It is similar to MESMOC plus, but it computes the entropy reaction in the space of inputs. It also needs to approximate the predictive distribution conditioned to Pareto set using expectation propagation, a very costly algorithm. We have performed two experiments. The first was a 4-dimensional input synthetic experiment with two objectives and two constraints. Here we display the results. We can see that both in the noisy and in the noiseless cases, MESMOC plus PESMOC under the couple variants achieved the best performance. The second was a robustness experiment with a 6-dimensional input, 4 objectives and 2 constraints. These are the results. We can see that MESMOC plus is more robust than PESMOC with respect to the number of Monte Carlo samples, because MESMOC plus performs better with fewer samples, but the differences between them become smaller as the number of Monte Carlo samples increases. In the execution time per iteration of MESMOC plus, PESMOC and MESMOC, we can see that MESMOC is the fastest method, followed very closely by MESMOC plus, but MESMOC plus performs much better. MESMOC plus drives the optimization process by selecting the evaluation that more reduces the entropy of the solution in the functional space. MESMOC plus approximation is closer to exact than existing methods. MESMOC plus can be used in a decoupled setting. It's competitive with other state-of-the-art methods for Bayesian optimization, but MESMOC plus is more robust and significantly faster to execute. Thank you very much for your attention.